Hey everyone, you know how everyone is talking about AI these days. ChatGPT, Gemini, Cloud, those are amazing tools that can write an essay, that can write a code, even sometimes having a conversation. And honestly, it feels intelligent, right? Like there is some super brain on there. But the surprising thing is AI, so especially this language models, isn't actually intelligent as how we think intelligence is. And today we are going to break down what is going on under the hood. So to get to the big stuff, let's start with the basic. What even is a language model? Well, basically, a language model is just a computer program designed to understand or generate a human language. Think of it like this. Its main job is to predict the next word in the sequence. That is, it is super simple, right? It is all about patterns and probabilities. Let's do a quick but simple example. If I say the cat sits on blank or dash, what is the most likely next word? Mat, right? Or maybe calf or maybe floor. A language model learns these probabilities by looking at ton of text. It sees a cat on the mat many times. So it learns that math is pretty good guess. Now, there are a couple of main ways this models learn. You have got what we call auto-regressive models. Those are like our example. They predict the next word one after the other based on everything they have seen before it. Think of it like always look forward. Then there are masked language models. Those are a bit different. Imagine you have a sentence and you had a word in the middle, like my favorite blank is blue. His masked model tries to guess what hidden words by looking at both the words before and after. So my favorite blank or dash 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 is blue. Most probably you can understand my favorite, then it is the first means the word before, and is blue is the word after. That means there is something missed between the favorite and the blue. So the LLM or language models can guess what words need to be filled in between my favorite and blue. That is color, as you know, most probably. And okay, it gets a float context. Both are super models, but for generating text, auto-regressive is the key. Okay, so we know what language model is. Now, what is an LLM? A large language model. Honestly, it is exactly what it sounds like. Really, really big language model. We are talking about a model with an insane amount of data and mind-blowing numbers of internal connections, or what we call parameters. That is the large part, actually. So why did they get so big? Well, it is a bit of a perfect storm, actually. First, data. We suddenly had access to massive amount of text data, the entire internet, basically books, articles, conversations, codes, everything. Second, parameters. These models have a billion, sometimes trillions of internal knob and deals that they adjust during training. More parameter means more complexity, more neurons they can capture, and third is compute. We got a powerful enough computers, especially GPUs, to actually train this colossal models on all that data. Without all three, LLM wouldn't be where they are today. Now, before we talk about how they generate text, we need to now about some crucial concept, that is token. See, computers don't understand the word like car or intelligence. They understand numbers. So when you give a text to the LLM, it first goes through something called tokenization. This tokenization breaks down your text into a smaller units called token. And a token can be a full word or a part of word or punctuation mark or even just a space. Example, the word unbelievable might be broken into unbelievable. Each token gets a unique number, and that is what the model actually processes. So with our text turned into numbers or tokens, what is the core idea? It is all comes back to what we said earlier. Next token prediction. The model looks at the sequence of tokens it has so far, and then it calculates the probability of every single possible token in its vocabulary. It is like it has a giant list of all possible tokens, and it assigns a percentage chance to each one, being the next best fit. Let's go back to our cat example. If the model has processed the cat set on the blank, it is not just guessing Matt. It is actually saying, okay, Matt has 60% of a chance, Coach has a 20% of a chance, Floor has a 10% of a chance, and Dog has 0.001% of a chance. And so on for 1,000 probabilities. Then it picks one, usually the most highest probabilities. Or sometimes it picks the slightly less probable one to make it sound more creative or less repetitive. And now here is an interesting part. How does we get a full sentence or even a paragraph from just predicting one token at a time? Well, it is a loop. The model predicts the first token, then it adds the token to the original input, and then it predicts the next token based on the new or longer sequence. It just keeps doing that, one token at a time, building out the response until it decides it's finished or it hits a certain length. It is like building a Lego tower, one brick at a time. Each new brick is chosen based on all the bricks already laid. So why does this process, which is essentially just really good pattern matching, feels so intelligent? Honestly, it is because these models have seen so much human language. They absorbed patterns, styles, facts, and even nuance from the billions of words. When you ask it a question, it is not understanding your question as a human sense. It is predicting the most statistically probable sequence of words look like an answer to your equation based on all the answers it sees in its training data. It's mimicking intelligence and incredibly well. let's quickly visualizing this whole thing. The user type an input or a prompt that gets broken into token. Those tokens go into the model, which is a giant complete network of probabilities. Then the model predicts the next most likely token, and the next and the next, until it forms the complete output. The response you see on your screen, simple is that really. So the big takeaway, the reality check is this. These amazing LLMs or large language models are powerful prediction machines. They are incredibly good at generating human-like text because they are learned the statistical relationship between words and ideas from vast numbers of data. But they don't think, they don't have a consciousness. They don't understand in the way a human does. And they predict and understanding the distinction and the thing. I think this is a super important as we navigate this exciting new AI world. Okay, before we talk about how AI works, I want to ask you something. You read the word cat, just you read it, one word, one idea, right? But here's the thing, AI doesn't do that, like at all, the way you and I do. AI doesn't read the text. And honestly, once you understand what is happening under the hood, it's the kind of change you just see entirely on the systems. Today, we are going to talk about tokenization, and I promise at the end of this video, you are going to look at AI response very differently. So, what even is tokenization? Let me break it down simply. Tokenization is the process of breaking text into smaller pieces before the AI does anything with it. That is, it is a simple version. You type something before the model even start thinking, and it takes your text and chop it up. This chunk is called tokens. Now, here is the interesting part. Why does this even need to happen? Why can't the model just read the sentence? Because computer doesn't understand language. I know that sounds weird for AI, but stick with me. Computer only understand numbers. That is all they ever known. So for a model to work with a text, that text needs to be converted into a number, and tokenization step is one of the most and the first conversation. Think of it like this. Imagine you are translating books into a secret code, and your code only has a numbers. First, you need to break the book into a pieces, then replace each pieces with a number. That is basically what is happening here. Okay, so what actually token is? You might be thinking, well, it is probably a word, right? And yeah, something it is, but not always. This is where it gets interesting. Token can be a word, it can be a part of word, it can be a punctuation, like a period or a comma. It can even be a space. The model doesn't see the sentence the way we do, and it sees the stream of tokens. Let me show you with example, because this is the part where it actually clicks. Simple one first. Take the sentence, hello world. That is probably two tokens, hello and world. Easy? Make a sense, two words, two tokens. Totally fine. Now here is more interesting one. The word unbelievable. You might be thinking, okay, one word, one token, but it is not. The model might be split it up like this. Unbelievable. Thus, 3 tokens, one word, unbelievable. 3 separate pieces, and honestly, this makes a sense when you think about how meaning is structured in the language. An is a prefix with it is our meaning, and able is a suffix. The model learns patterns at this level, which is actually really useful. So this brings us to the types of token you will see. These are basically 3 main categories. First is a full word. It's common every word, everyday work. It's like the, is, and cat. These are usually their own token. They appear so often in the model has them backed in. And second is subwords. These are a part of words like an, ing, tion, or able. Less common or longer words get broken into the chunks. It's how the model handles new or rare words without completely losing its mind. And the third is punctuation, like periods, commas, question mark. Those are their own token too. Even a simple exclamation mark has its own token. Okay, now here is the important part. Once the text is split into token, each token gets assigned a number, a unique ID. This unique ID is called token ID. So hello might become 9906, world might become 1917. These numbers are what the model actually works with. Text goes in, number comes out. The model does all its thinking in numbers and then converts back to the text at the end. Now, these IDs don't come out of them just from air. The model has something called vocabulary. Think of it like a giant dictionary. A fixed list of all the tokens the model knows. GPT-4, for example, has a vocabulary of around 100,000 tokens. Every possible chunk of this token model can work with in that list. If a word isn't in the vocabulary as a whole word, it gets split into a subword that are. That is the beautiful of this system. It can handle almost anything. So why should you care? Like, why does this matters particularly? Honestly, it matters more than people think. First, cost. Most AI PIs charge you per token, right? Not per word, not per sentence. It is just per token. So if you send a long prompt and it generates a long response, you are paying for every single token in both. Understanding this helps you write more efficient prompt and save money. Second, speed. Processing tokens takes a competition. More token means more work for the model. Shorter is cleaner input in general gives you a faster response. And the third, a context length. Every model has a maximum number of tokens it can hold at a memory at once. You might be hear a phrase like 128K context window. That is 128,000 tokens. That is the limit. If your conversation or a document exceeds that, the model literally cannot see the earlier part anymore. It just forgets them. Here is something that trips people up. Rare words, technical terms, names from the language, really long words. This almost always gets broken into more tokens than you would expect. Like if you write a prompt, a full medical terminology or a code in the obscure programming language, you might be using a way more tokens than a plain English version of the same idea. And that hits your cost, your speed, and your context window all at once. This is one reason why simpler, cleaner language often works better with AI. Not because the AI is smarter with a simple words, but because it is literally more token efficient. So let us zoom out. Here is how it fits all together. When you type a message to an AI, any AI, it doesn't see your words. What happens is your text gets tokenized, thus tokenized tokens convert to ID or token ID. Thus token IDs, thus numbers are literally the input to the model. The neural network processes the numbers and does it things and produces a sequence of numbers back. These numbers are decoded back into a token, and a token are assembled back to a text. That is what shows up on your screen. At no point did the model read your sentence the way you would. It never saw the word hello. It saw something like 9906. The whole experience of AI reading and understanding you is built on top of numerical layer that the most people never think about. So next time you open the ChatGPT or Claude or any LLM, start typing. Just remember that's what actually happening in the fraction of a second before the model even start thinking. Your words are being broken apart, tagged with the number, and fed into a system that has never once seen in the world the way you do. It doesn't read, it doesn't hear, it processes the sequence of numbers incredibly fast at a massive scale and produce a sequence of numbers back. And that kind of the will, when you think about it, all of that intelligence, all of the response that you feel so human, they start with this one glamorous step. Before any intelligent, before any answer, everything's become tokens. Okay, if you found this video helpful, or if it clicked that didn't before, please just hit the like button. That genuinely helps this channel to grow. And if you want to learn AI concepts practically, please make sure that you subscribe. I will break down the. So in the last video we have talked about tokenization, how AI break text into a piece of words, how the word is getting the ID or token ID. Both are fine, and honestly there should be one question is right back in your head. Just a word is a number, just actually anything. Like if I tell you a cat is 284, that the number 284 doesn't tell you any meaning. A cat is an animal. It doesn't tell you that cat and dog are related. It doesn't tell you anything at all. It is just a label. So how does AI got from that list of meaningless number and actually understanding the language, knowing that happy and joyful are similar, or that the word bank means something completely different depending on the sentence? That is what we are going to figuring out today. And honestly, this journey from raw numbers to actual meaning is one of the most elegant ideas from all of the modern AI. And let's get into it. Before we get to the text, let me give you a quick introduction with image, because images are actually this part and pointing point. So you have a photo of cat. What is the photo? Really, to the computer, it is a pixel, a grid of dots, and each dot has a color, and the color is just 3 numbers, one red, one for green, and one for blue. So 100 by 100 image, that is 10,000 pixels, each with 3 values. So 30,000 numbers, that is the whole image. And here is the thing. This mapping is natural. More light means bigger number, less light means the smaller number. There is an actual relationship between the number and what it represents. The AI can work with that. It can learn that is this arrangement number of usually means cat or car or a mountain. So image to pixel, pixel to number, clean and initiative. Now text. This is where it gets more interesting because text doesn't have that natural mapping. With text, you have words. Word become token, its ID. And we covered that in the last video. So the cat sat on the mat become something like, okay, so we have a numbers, but here is the problem. This is the reality important. These numbers are arbitrary. Good might be token 6, bad might be 22, or great might be 21. No mathematically bad and great looks like together. Good is like an outer, but the completely wrong semantically. Good and great are similar, bad opposite. The model has no way to know what. It is just sees a number and it draws completely false conclusion from the proximity of the number. So token ID alone, they give us an identity, but no meaning, no relationship, nothing. We need something better, and people tried a few things before they lands on a real answer. The first real attempt was one hot encoding, and the idea was to fix that false ranking problem. Here is how it works. Say your vocabulary has 5 words: cat, dog, bird, fish, and lion. Instead of giving each word a single number, you give each word a vector, a list of values, all zeros except for one position, which is 1. So cat is 1 0 0 0 0, dog is 0 1 0 0 0, bird is 0 0 1 0 0. Now no word has higher or lower numbers than another. No false ranking. Every word has just different slots. Problem solved, right? Well, a kind of. But here is the issue. In this system, every single word is equal distance from every other word. Cat and dog looks just different as cat and justice. The zero sense of similarity. The dot product of any two words is always 0. Always. The model is completely blind to the fact that cat and dog are both animal. The good and great mean similar thing. In practically speaking, real vocabularies have 50,000 words and more. So every word becomes a list of 50,000 numbers with exact 1 and 49,999 words, zeros. That is incredibly wasteful, conceptually expensive, and still semantically empty. So one hot encoding fixes the ranking problem, but it creates a new problem, semantically neutrality, no meaning anywhere. Okay, next attempt. What if we look at the whole document instead of individual words? This is a bag of words. Imagine literally taking all the words in the document and throwing them into a bag. Shake it up. Now count how many times each word appears. That count vector, that's your representation. So for the cat sit on the mat, the shows up twice, cat once, sit once, and so on. And this actually works reasonably well for some tasks, like spam detection. If an email contains free, win, praise, and click even without knowing the order, you can probably guess it is a spam. The frequency pattern is enough. Now people extended this diagram. Instead of the single word, you count pairs. The cat set on. You are capturing a little bit of local order now. And n-grams go further. Triple, quadruple, longer sequence. But here is the honest limitation. As n gets bigger, your data gets incredibly sparse. Most n-gram combinations never appear in your training data. And you are still just counting. You lost the overall order of this. Dog bites a man bites a dog. Some word, some count. Look identical to the back of the word model. Completely different meaning in reality. And long-range relationship, no chance. A trigram has no idea that word in the position 2 is connected to the word in the position 15. It just counts C that far. So bag of words gives us a frequency, still no real meaning. Now here is we hit the real problem, the one that all the method completely fail at. Consider this sentence. Sarah enters the old library. She knows something was hidden behind the desk. When you read it, your brain is doing a lot. You know old is describing the library, not Sarah. You know something is probably hidden behind a bookshelf or a wall. Because of the context, library, dusty, and hidden. You are doing semantic interference. You are using meaning and context together. Now, take a word bank in two sentences. I went to a bank to deposit my check, and we sat by the river bank and watched the sunset. Same word, completely different meaning. And a bag of word model exists. Bank was time and treats them identically. It has absolutely no mechanism to distinguish this. Or he was cool about the whole thing. Is a cool, calm, a stylish, or a cold? You need a context now. A truly useful representation needs to satisfy one key principle. If you replace a word with a synonym, the meaning of the sentence shouldn't be changed much. The mathematical representation should reflect that. Happy and joyful should be treated similarly by the model. None of those methods we have seen can do that, right? Not one hot, not bag of words. So the field needed something fundamentally different, and that something is word embedding. Here's the core idea. What if instead of representing word as a single arbitrary number or a long square list of zeros, we represent it as a dense list of numbers, where those numbers actually capture meaning. Like, what if cat was representing us? We might be notice those are really similar. That's the whole point. Words with a similar meaning get similar vector. Words that are unrelated get very different vectors. The distance between vectors reflects semantically similarity. Close vectors, similar meaning. Far apart vectors, unrelated meaning. Now, here is the beautiful part. Think about it with Excel. Imagine dimension for gender, dimension for reality, and dimension for power. King, high reality, male, high power. Queen, high reality, female, high power. Man, low reality, male. Woman, low reality, female. In a real embedding space, you have hundreds of those dimensions, not manually labeled, but automatically discovered by the model during training. The model figures out which dimensions capture useful distinction. You never tell it what it actually means. It discovers them on its own. And because of this structure, you can do math on meaning. King minus man plus woman equals queen, and almost exactly. Take a Beijing minus China plus Japan. You isolate the capital city concept, and Japan, you get a Tokyo. That is not a trick, that is geometry. That's the relationship encoded in number. Okay, let me make this visual because I think this is where it really clicks. Imagine a big space, hundreds of dimensions, but let's just think of it as 3D room for now. Every word is a point in that room, and a word with a similar meaning are clustered together. In one corner, all the animal words cat, dog, bird, lion close together. In the other corner, emotion words happy, sad, hungry, and can close together. Country name cluster, food words cluster, action words cluster. Now here is a famous example. King, queen, man, and woman. Draw a line from man to king. The direction, the arrow represents something like royalty, like being elevated to the top. Now take that exact same arrow, put it into the woman, follow the same direction. You land right into next to queen. The relationship is preserved. The geometry holds. Researchers actually visualize this. They take these high-dimensional vectors and use a technique called PCA to squish them down to 2D, just so we can see them. And you literally see a cluster forming. Tense terms grouped together, number words together, cat species together. The model discovered all of this just from reading text. So how does word to vector learn these vectors? Here is the intuition. The foundational idea is this. You can understand the word by the company it keeps. If the coffee always appears near the word like morning, hot, cup, drink, the model can learn what coffee means just from that pattern. No dictionary, no manual label, just context. Word to vector uses two approaches to do this. One is CBOW, continuous bag of words. Given the surrounding words, predicts the middle word. So if you see I drink blank in the morning, the prediction will be coffee. The context predicts the center. The second is skip gram, that's the reverse. Given a center word, predicts the surrounding context. Given coffee, predict hot, morning, cup. Both approach train in the model to get good at this prediction. As a side effect, the internal numbers the model used to represent each word start into encoding meaning. Words that appear in similar context end up with similar vector. The model figures it out entirely on its own, just from patterns in the text. That is, no human label, no rule, pure statistical pattern recognition that shows capture real meaning. Okay, so where do embedding actually live in a modern AI model, like in ChatGPT or any transformer? Here is the flow. We give the model a sentence, it gets tokenized, broken down, and the token ID. Thus, this gets into the embedding layer. Think of this as a giant lookup table. You give it a token ID, it gives you back a vector, and this list of numbers that represent the word's meaning in the model learned semantic space. So a cat token ID 284, embedding vector is 0.2, 0.5, 0.8, 0.1. This looks up a table, and technically called embedding matrix. Has one row for every word in the vocabulary, the number of columns in the embedding dimension. So for the vocabulary of 50,000 words and embedding size of 512, you have a matrix of 50,000 by 500 numbers. Every row is a word, every column is learned dimensions. And importantly, unlike word to vector, which is often pre-trained separately, in a transformer, this embedding layer is trained end to end. The whole model learned together, optimizing for the actual task. This embedding layer is very first thing that happens in the transformer. Token become vector, then it is real processing bigger. But we have one more problem. A transformer processes all the tokens at the same time in parallel. not one by one, left to right, all at once, which means it has no idea what order the word comes in. Dog beats man, man beats dog. The same embedding, the same everything. The model literally cannot tell you them apart. And order matters enormously in large language models. Obviously. So before feeding the embedding into the model, we add something called positional encoding. Here is how it works. For every token, you generate a separate positional vector, a list of numbers that encode where the sequence this token sits, position 1, position 2, position 3, or position 7, whatever it is. Then you add this positional vector directly to the world embedding vector. Now here is the thing. And this addition doesn't change the size of anything. The dimension stays the same. You are just adjusting the value. The meaning and the position are now blended together in a single vector. So cat in the position 1 looks slightly different from cat in the position 7. Same word, different position, different final vector. The model can now distinguish them. Word meaning plus position combined to one vector. That is what actually gets into the transformer. Okay, let us zoom all the way out. We started with a core problem. Words are not numbers, and AI needs numbers. First, we tried token ID. Simple, but they implied false relationship. Then one-hot encoding solved the ranking problem, but created a semantic neutrality. Every word equally unrelated to other word. Then bag of words. Frequency is useful, but order disappears and the meaning is still missing. Then finally, embedding. Word become a dense vector. Similar meaning sits closer together in the space. Suddenly, the model can do something remarkable. It can reason about relationship. King minus man plus woman equals queen. Beijing minus China plus Japan equals Tokyo. Meaning, genuine semantic meaning. Encoding the geometry and distance and directions in a mathematical space. And in transformer, those embeddings get positional information blended in. So the model knows not just what each word means, but it knows where it sits in the sentence. That is the foundation. That is how AI moves from route symbol to something that starts resembling understanding. But I wanted to leave you with this. Standard embeddings are still static. The word bank gets the same vector whether it's next to the river or next to the money. Meaning is global, not contextual. That gap, that's exactly what the attention mechanism solves. And that is what we are getting into the next time. So last time we have seen word embeddings, and we saw that how word becoming a vector, king minus man plus woman gives a queen and works mathematically. And we ended up with one problem. Embeddings are static. They don't understand what the word bank is, whether the sentence is about a riverside or whether it's a financial institution. Because embeddings can capture a global meaning but not contextual meaning. And today the question is how models can fix this problem. How they are capturing the word bank in the relevant context. And the answer is attention. And honestly, once you understand what attention is, it is hard to unseen. This is Salamlak, and this is a video all about attention that next to the last video embedding. Let's get into it. Let me make the problem more concrete. Take this sentence. The animal didn't cross the street because it was too tired. What does it refers to? The animal, right? Not the street. You know that instantly. But how? You looked at other words in the sentence, animal, tired, and you connected them to it. You paid more attention to some words than others. Now take the animal didn't cross the street because it was too wide. Same structure, but now it refers to the street, not the animal, because wide fits a street, not an animal. Your brain is consistently doing this, weighting which words are relevant to understanding each other words dynamically based on the context. That is exactly what attention mechanism teaches an AI to do. So here is how self-attention works. And I will keep the math slide. Just an illustration. For every word in the sentence, the model asks three questions. One, what am I querying for? What information do I need? That is query. The second, what information am I offering to the other? That is the key. And the third, what is my actual content? That is value. Think of it like search engine inside the model. When processing the word it in our sentence, the query says, I need to find what I refer to. Every other word offer its key, like a tag saying, here is what I am about. The model compares the query against all the key words that match get the higher score. Animal score high, street score low in the first sentence, and the second sentence third score high. Those scores become white, and then the model takes a weighted combination of all the values so it gets updated. It absorbs meaning from the word most relevant to it. The output is no longer a static embedding, it is contextually updated representation. The word bank near the river will end up in the completely different place in the vector space than bank near the money. This is where static embedding becomes dynamic. This is the fix. Now, here is the interesting part. Standard self-attention lets every word look at every other words, past and future. But when you are generating text like GPT is doing, you can't look at the future words. You haven't written them yet. Think about it. If the model is predicting the word or the next word, it shouldn't be allowed to pick the head at what comes later. That would be cheating, right? So we use casual self-attention. Same mechanism, but with masked applied. It is really simple. The model is blocked from attending to any word that comes after the current position. Word 3 can see the word 1 and 2, but cannot see 4, 5, and 6 and on. This masking is visually implemented as a triangle. The upper half is blocked, the lower half is open. Each word can look only backward at the word that comes before it. This is what makes language generation possible. The model builds understanding left to right, one token at a time, never cheating by looking ahead. Okay, so we have self-attention, but here is the next question. What if only one type of attention isn't enough? Think about the sentence like, John gave Mary his book because she asked him. To understand this sentence fully, you need to track multiple things at once. His refers to John, she refers to Mary, him refers to John again, and the book is the object being transferred. Once the attention pass might focus on the gender refers, another attention might track the action, another attention might focus on who owns what. That is multi-head attention. Instead of running attention once, you run it multiple times in parallel, each time with different query, key, and value projection. Each head learns to focus a different type of relationship. One head tracks semantics, another head tracks coherence. Who refers to who? Another might track positional pattern. Then at the end, you take all these outputs and combine them, concrete them together, and pass through them one final transformation. The result is much richer representation. The model isn't just looking at one relationship at a time, it is tracking many simultaneously. Okay, now let's see how all of this fits together in actual transformer. Here is the flow from the beginning. You put a sentence and it gets tokenized. Each token gets embedding, that means vector, positional embedding, the positional encoding get added, so the model knows order. Now this vector goes into transformer block, and inside the block, the first major thing that happens is multi-head casual self-attention. Every token attends to every previous token, and contextual representation gets built. After attention, the output goes through the feedward network, a few layers that process each token updated representation independently. Think of this as a model doing additional reasoning after gathering context. And this whole block, attention plus feedforward, gets stacked. In GPT-2, it is stacked 12 times. In larger model, many more times. Each layer refines the representation further. Lower layer might capture semantics, who is doing that, what. Higher layer capture more abstract semantics, what does this sentence mean, what is the intent behind it. By the final layer, the model has built deeply contextual understanding of every token in the sequence. Okay, let's make this ready. Let's talk about GPT-2 specifically. GPT-2 is a decoder-only transformer. That means it uses casual self-attention, and it only looks backward, never forward. And it builds for generation. Here is the architecture in plain terms. Token embeddings plus positional encoding, that's the input. Then 12 transformer blocks stacked. Each block has multi-head casual self-attention with 12 heads, and followed by the feed-forward network. Then the embedding dimension is 768, meaning every token is represented as a vector of 768 numbers throughout the whole model. At the very end, the final layer maps that 768 dimensional vectors back to the vocabulary size. It produces a probability score for every word in the vocabulary, and the highest probability becomes the next predicted token. And that generation, the model produces one token. That token gets added to the input. The whole process runs again. Another token, again another token. Auto-regressive generation, one token at a time, each one informed by everything that comes before. So let's tie the whole arc together across both videos. Words become numbers, that means token ID, and token ID become embeddings, that means dense vectors encoding meaning as a geometry, and embedding plus positional encoding gives the model meaning and order. Then self-attention made the embedding dynamic, and each word updating its representation based on the words around it. And casual attention made the generation possible, respecting the left to right constraint, and multi-head attention let the model track multiple types of redshift simultaneously. And stacked transformer blocks like GPT-2 built layer after layer of increasingly abstract understanding. From raw sentence to deeply contextual, semantically rich representation, that's the full journey. And here is the thing worth remembering. The model never got told what any of this means. It discovered semantics, reference, and context, all of it, just from predicting the next token word over and over on massive amount of text. Next time we will go even deeper into how transformers are trained, loose functions, bug propagations, and how the model actually learns from its mistakes. And if you found this video helpful, please make sure that subscribe and hit that like button. It really helps the channel grow. And see you there. Thank you very much.